Hello? Okay. So, I'm Bruce. I work in MSRC Engineering. We used to be known as SWI, but they just recently rebranded it, so now we're known as MSRC Engineering. MSRC Engineering is the group that when people report bugs to us, when people report bugs to secure@microsoft.com, it gets a case manager, and then gets assigned to one of us, and we triage them, and we make sure that the patches are done correctly. Today I'll be talking about how to analyze target attacks with Office documents. However, before I start, this is the first time I've been to a European country, so this is also the first time I've been to CCC, obviously. So there are a lot of pretty interesting things. Yeah. So this is like probably the most unique event I've ever been to. The cool thing downstairs, the hacker space or whatever. If you guys are watching, great job. Next time an FNet server goes down or get owned, I'll know why. And for those of you who work in governments or whatever, hello. All right, and I want to thank Felix and Fukami and the rest of the CCC staff for having me here. You guys are great. So we'll start. So most of you are probably familiar with target attacks. So basically what people do is, these are not drive-by attacks or anything. Most of the time the attackers will have an idea of who they want to attack, and typically these are large corporations, and they figure out, they do reconnaissance on the victim. They figure out who they work for, what kind of work they do, and sometimes even like their reporting infrastructure, their organizational, where they are in the org. Like, for example, if they're a manager or a director and so on, and who works for them. And based on those, on the details that they have, they can craft a special document and spoof it so that it looks like it comes from somebody they know, and then they send it to them and they'll obviously open it. So it's been very popular in the last few years. You hear some of the headlines I was able to find. Security Focus and Computer World are most trusted sources for computing news. So it is quite popular, but there's not much technical, like a lot of technical details, or even how to analyze these things in the public. I'm not sure why, but today I'll show you how to do that. And also I'll be releasing a new tool to help analyze some of this stuff. So using Office documents as an attack vector is like one of the best attack vectors that you have, because one, everybody uses Office. If you work in a large company, everybody uses it. And so people, if you work in a large company, you receive, attachments every day, especially if you work in HR, people submit resumes to you, quite often. And so it's quite common. People, if you send them an EXE, obviously it gets filtered at the exchange, mail gateway. So most people, back in the days that you just attach a Trojan, it's like, hey, run this, and you get free, you win the lottery or something, like free porn or something, and people click on it. So nowadays, they block executables at the mail gateway, so that stuff doesn't work anymore. So the new style is you attach like a PDF or a Word document, and then of course these things are so natural, people receive them every day, so they just click on them without even thinking. I mean, I would do it. And a lot of these things they're malicious, right? So, and they're very difficult to detect. Everybody has, most large companies have antivirus and firewalls and all this blah 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 at the border to try to protect themselves. But when Office documents come through, they don't filter them, because if you block them, like half your org might not work anymore. So it's very difficult to detect. Traditional perimeter security, like firewall or whatever, it's not adequate. It's not sufficient. And also there's a lack of tools and techniques on how to triage these things. All right. So before I go into the details of these attacks, I just want to say that in order to understand them at a concrete level, you actually need to understand the Office file format. Without them, you might still be able to triage them, but you won't be able to get it. You won't be able to understand it fully. So I'll start first by explaining the Office file format. And the file format I'm referring to is the binary file format, the one that we released the specs for in February of this year or something like that, thanks to the EU. Yeah. And so, and when before that, there was no public documentation except for like the OpenOffice team. They did some reverse engineering and they wrote some documentation about it. And it's actually quite excellent. So if you work for OpenOffice, great job. Yeah. So the binary file format is the file format that Office 2003 and below produced. Office 2007, they don't use that anymore. They use the XML file format because I guess it's in style nowadays. So anyways, and they follow this, the file format is called like the structured storage file format. And it's implemented as compound files. And all it is just a file system inside a file. So you know like SQLite, you have a SQL like database inside just like one file. This is like a file system inside one file. And so you have the concept of directories and files. So except they're not called directories and files. They're called storage and stream. So storage is the equivalent to a directory, and a stream is a file. And each Office application stores its own data in a specific stream or storage. They'll give it its unique name. And when Office parses these documents, it just opens it up, figures out what the stream names are, and it reads those streams. That's pretty much it. It's very simple. Parsing it by hand is like not difficult, but it's annoying. It's difficult to make a good implementation of parse it from scratch. And this is why we have a COM API. We have COM API to deal with these files. Oh yeah, before I go on, so OLESS files are not only used by Office, they're actually used like MSI files, OLESS. Like a lot of third-party applications use these things. So it's not just Office. And most people, you shouldn't be writing your own OLESS parser. So we provide a COM API for you to do that. And basically all you do is you call a function called like STG open storage, and you pass a file name. And then you tell what kind of mode you want to read it in, like read, write, blah, blah, blah. And then you enumerate all of these storages and streams. And then you can go through them and you can read them. This is very similar to, like for example, in Unix you have open, read, and blah, blah, blah. It's the same thing, except for it's in Windows. Yeah, so this is an example of in how to use the COM API. But if you don't know C or C++, which that's only probably like 1% of you guys or something, you can use Python. I actually like Python a lot, so yeah, go Python. Python has, there's a class called Python COM, and part of that is just a port of, it calls the Win32 API. And so it's the same function names. And all you do is you pass the file name, enumerate elements, and you iterate through, it passes you back a list, and you iterate through it, and you read or write from it, do whatever you want with it. And that's it. Is there a question? Okay. So if I'm talking too fast, please let me know. So this is an example. This is an example in Python. It's like, I don't know, like 10 lines of Python or something like that, contrary to like 30 lines in C. So it's good. So that was just the basic details of how to read an OLESS file. Inside the OLESS file is the Office file format. So I'm going to go through the example of PowerPoint, mostly because it's popular and it's the easiest one to explain. So PowerPoint, which is what I'm using now. So PowerPoint stores all of its data, like the slides and all this stuff, inside a stream called PowerPoint document stream. And so to open this stream, all you do is you call open stream. Like, you'll STG open storage the file name, then you call open, it passes back an object, then you call open stream on PowerPoint document. And it passes you back an iStream object, and then you read the data. And the PowerPoint file format also is kind of like a file system as well. It has a container and atom. A container is a directory, and an atom is a file. And the format's also like TLV style. So this is the structure from the PowerPoint. I think this is from the PowerPoint source code. I can't remember. But basically, the way it's a very small structure, and the way you can figure out if a structure, if a record is a container or an atom, is just based on rec version. If it's equal to OXF, then the record is a container. Anything else is an atom. And the record type refers to the PowerPoint specific record types. And these are the records that we document in the file format spec that we released. And so all you do is like you figure out what the number is, and you open up, you download the PowerPoint file spec, which is about like I don't know, like 400 or 500 pages long. And then you go to index, you figure out, you click on the number, and you go there, and they tell you what it is and how to parse it. This is a picture of it. I drew this using Xfig. So yeah. So it's pretty easy. You have a version, instance, a type, data length, and then more data. This is standard TLV style, which most of you guys should be familiar with. And to parse it, so basically what you do is when you read a stream, the first thing is a header, in which the header is the structure. And then you figure out, okay, is this an atom or is this a container? If it's a container, then it'll tell you that how much data is there. And then you read the next block, and then you continue. You do it recursively until you've parsed all of the data. I also do this in Xfig. This is pretty cool. And this illustrates how our internal PowerPoint parser works. So it's pretty simple. This is just in case if you decide to like write your own PowerPoint parser, and you want to validate if your parser is working correctly or not. This is a picture of what a PowerPoint document looks like. The first thing the first record that you'll typically see is a document container, which is type OX3EA. And inside that container, you have document atoms and an environment, blah, 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 blah. And then you have like slide containers. Slide containers, so each slide in PowerPoint is described using a slide container. So like the header, the footer, all the data, page number, everything is inside the slide. So if you have like 20 slides, you have like 20 slide containers. So that's pretty much it. It's pretty easy to understand. So this is an example, for example, like the document atom, which is the second one on the list, like 3EA. Here it is this is a spec. This is a copy and paste from the official PowerPoint spec. And so this is just a structure. So you just type that out and you read it. That's it. This is a slide atom. They show this. That's what it is. So it's pretty easy. This is an old version of the PowerPoint spec. By the way, if you notice, it's only like 118 pages. This is actually the first version of the PowerPoint spec. These specs are actually updated frequently, sometimes even on a monthly basis. So if you download the PowerPoint spec now, it's like, I think 400 or 500 pages. So, I know, it takes time. All right, and so parsing. So if you intend to write your own parser, you have to understand that you can't just call, get a file handle and then read it. You can't just do that because it's a file system, just like standard file system, you have fragmentation. For example, if you open up, you edit your PowerPoint slides a lot, they will become fragmented. And obviously, that implies that raw consecutive bytes does not necessarily mean that they're part of the same record, right? So to do it properly, you got to treat it as a stream, an only stream unit. And to do that, I just told you use a COM API, or you can do it manually. You read a header, and then there's a OLE header, and it tells you, how to locate the streams and how big they are. And this is the OLE file format is specified in a different spec, which we also released. There are another one. That one is only like 12 pages. Just in case you don't understand that one, the OpenOffice team has one as well, and that one is like 30-something pages, and it has pretty good, elaborate information on how to implement it. So it's pretty good, and yeah. And the third choice we have is you can integrate all this into a hex editor, so that you can view like the text and you click on it and you say, oh, and the hex editor will tell you what record this is. So there's a hex editor called Hexer by Sebastian. If you're here, yeah. So I love everything about Hexer, with the exception it's written in Java, but it's okay. The cool thing about Hexer is that I actually use it, and no, sorry, that didn't come out right. The cool thing about Hexer is that the cool thing about Hexer is you can actually write plugins to it using either Java or Ruby. Pardon? Python too, I guess. Okay, yeah. I talked to Sebastian a couple days ago, and he said that he'll probably implement some of this stuff in Hexer pretty soon, so you probably don't have to do it yourself. So, yeah. So Hexer is good, you should try it. That's not like marketing, yeah. So anyways, and so the tool that we're going to release is called OffVis, and it's actually like a Office it's a visualization tool, and it parses any standard OLE file, and it has the capability of defragging the file system for you so that you can parse it manually. So I'm going to demo that. Hopefully it works. Let's do this one. So here, like like on the left side, you see the root entry. The root entry, you can see like PowerPoint document. This is the main one, and you click on it, just selects it, and then this one is not too fragmented, but you can go to Tools, and you can defrag it, and then you can save the file. And the reason why this is useful, you might think, well, what the hell? I can just do this in Python, right? The reason why this is useful is because if you want to write a parser from scratch in your hex editor, you want to treat the hex editor doesn't have a concept of streams, right? So it just notes at consecutive bytes. But if you fragment the file, then the consecutive bytes means I'm going to be part of the same record. So you can parse it that way. So that's why this is useful. So we'll probably release this. We don't know when it's going to appear, but we'll release it to the public, probably on our blog or something like that. Did someone ask, is this going to be open source or something? Oh. Yeah. Yeah. And so, yeah. We probably won't release the source code for it because it's pretty simple, and most people could probably decompile it anyway, so it would be like an offense to do that. Yeah. No joke. I mean, this is .NET, right? So now I'm going to show you an exploit demo. I'm not going to show a real one because I guess I'm not supposed to. But this is a simulation of what a real exploit will look like. So they typically come in email, and so they'll send it to the person. In this case, I'm going to use myself as the victim, and the attack is going to be like the CCC staff. So most people, they'll probably know that I'm attending it because you can read it on the website, and they'll send an email saying, oh, hey, Fukami Fleet says that you're coming here, so here's a list of things that you should see. Nice, we'll see you there. So obviously, I'll probably click on this stuff because it makes sense, and so I'm going to click on it and see what happens. So it's going to be like, normally I would have Outlook set up, but that's too much work and it's not really necessary. So I'm just going to double click on this. And here, bam, right? You notice? Here you notice it opens a clean document with the name of various, I guess, popular tourist spots. I don't really know what these are, by the way. And then it launches calc.exe. This is obviously a demo. In real life, they'll drop a typical rootkit or some type of Trojan, and you obviously you won't see it. And to a normal user, I ran this in a VM, but to a normal user, it'll be like very fast. If you run a real machine, you won't even see it. If you notice, you saw it quitting and then restarting, right? That's because the VM is slow. So, but in real life, you won't even notice it. So, anyway, so that's how it works. That's what it looks like. So, yeah. And I mean, even though that was a fake example, this type of attack is quite common. For example, I've seen attacks where people will send an email to somebody and say, "Hey, check out my vacation pictures." And then they'll attach typically a PowerPoint or a Word document which will include pictures, and they'll open it up. So this is not far from reality. All right. So the defensive mechanisms. How do you protect yourselves? Always have the latest security updates. I guess it's kind of obvious. One thing I should bring up is most consumers probably won't be affected by this because consumers have they turn on Windows Update, so you get the patches automatically. So most of the time you'll be okay. But sometimes large corporations, not everybody can patch on the same day, right? So they don't always have the latest patches, so they get owned. So The other option is if you have Office 2003, just like you install Service Pack 3, which is we released like in December or something like that. It's free, and basically SP3 is the result of a major security push. We fixed a lot of bugs there. And one fact is, if you have Office 2003 SP3, then you would not be vulnerable to any of the quote-unquote zero-day exploits that was acknowledged in the public. In fact, I've never seen one that affects Office 2003 SP3. We have seen bugs that affect 2K3 SP3, but I haven't seen like real exploits that work on it. So if you have Office 2003, just install SP3. The next one is you can use Moleyes. Moleyes was actually written to fix these target attacks, but not everybody can use them. It requires at least Office 2003. And the way it works is quite simple. It converts the binary file format to the new XML file format, and then reopens it using the XML part, the Office 2007 parser. So there's no more bugs there. So yeah, yeah. And this is why when you download Moleyes, they'll tell you you need to download the Office 2007 compatibility pack, and that's the reason why. And if you use Office 2003 SP3 and Moleyes together, I would go to say that it would mitigate many of the Office bugs. I want to say all, but never say never, right? So, but it's quite effective. And this is one of the main reasons why we list Moleyes as a workaround on a lot of the Office bugs that we patch, on the Patch Tuesday. And the last one, use Office 2007. Yeah. So I won't say too much about that. And to be fair, I want to say that it's not just Office that's being exploited. Adobe PDF, it's also quite common. In fact, in the last couple of months, PDF target attacks using PDFs as attachment is quite popular, and it's actually on the increase. I wonder why, but yeah. All right, so we're going to the exploit structures. Now, I'll show you the file format, a demo of what the exploit looks like when you get owned, and how to defend yourself. Now we're going to the analysis part. So the exploit is actually quite simple. It's nothing out of the ordinary because it's just another bugs. Most bugs, it's not like a bug in Office is different from a bug in I don't know, Win32K or something. It's mostly like memory corruption. Sometimes Office will actually read a number from the file and then use that to calculate some pointers, and without checking that number. So you can change the number, do whatever you want with it, and you'll ruin Office or something. I don't know. Anyway, so the basic structure is you'll have shellcode, which is all exploits have them. And then you have a malware component, which is attached to typically the end of the document. Sometimes it can be in the middle of the document. It varies. And then you have a clean document, which is what the victim sees when the exploit runs. So in this case, in the case that I have, the clean document was the document that had those list of tourist spots. And I'm going to go into the techniques. The techniques are actually not too special, but some parts are unique. So this is a picture, an abstract picture of what it looks like. So in the top, you have an OLESS header, which all OLESS file has. And then you have some Office records. And then you'll have some shellcode. And then maybe you have some more Office records. And then towards the end, you'll have a piece of Trojan or malware. In this case, I only show one picture, only one Trojan or malware. But in some cases, you can have up to two. They can have like 2 or 3. I don't know why, but they're multiple. And then towards the end is usually a clean document. But then, of course, you can always swap these things around. They can be variations. But the important thing is, it's all delivered in one package. It's one document. Everything is inside. They don't have to phone home to download a Trojan or whatever. So it's very convenient. And also, it bypasses AV detection, because the AV file, they're not going to scan the Office document. If they see an exe field and a trigger, they're not going to do that. So, because sometimes people do insert these things there for legitimate reasons. So. Okay, so the techniques they use. The shellcode is pretty simple. You use standard get EIP, so they'll do jump call pop, or use the FNSTNV instruction. They'll have custom encoders. Sometimes the shellcode won't be encoded, so you can actually spot it pretty easily. But 99% of the time, it'll be encrypted. So you'll just have like, a decoded stuff, which is probably maybe about 20, 30 bytes, and then the rest is all like, obfuscated / encrypted or whatever. And it uses just very standard Win32 shellcode, pub retrieval to get the base address of current 32, because we don't do syscalls through int80 like we do in FreeBSD or Linux. And then the last two characteristics are fairly unique. One is file handle brute force and application relaunch. File handle brute force, I'll explain next. Application relaunch is what happens when they call exit process on the exploited process, and then they call winexec to reopen it, and that's what you saw when I double clicked on it. You saw if it popped up and then exit and then reopen again. That's the application relaunch. Sometimes it crashes, but still works. But nowadays the attackers are pretty smart people, so it doesn't crash anymore. So why do they need to use file handle brute force? The reason why is the exploit needs to find itself in memory, and by this I mean not get EIP, but to find the physical the physical contents of the file. They need to find that, and in order to do that, you need to get a file handle to it. So the other way they can do it, they can scan the entire process space and look for sentinel values, and then say, oh, once I see value OX123, oh, I know that's my file, and I'll start parsing. But in reality, that doesn't work because the entire process space is very big, and you don't want your exploit to take too long because people will get impatient. They'll just close it. So so this file handle brute force method is very simple and very short to implement in assembly. It's probably about maybe 6 instructions or so in assembly. And the way that's all I do is they start from file handle 0 and they call get file size on it, and then the get file size will return a value, and then they compare that value to a known value, because they already know what the exploit file size is like. So once they know the file size and they compare it, and you get a file handle back and the file size is the same, there's a high the chance of it's probably the same files that they use. So, and inside that file, they already know exactly where the offset of the Trojan, the offset of the clean files, so they can just fseek to it and extract it. So anyways, that's how it works. So this is a summary of the exploit structure. There can be variations. I just want to make sure that I say that. So the shellcode decodes itself, and it jumps to a decrypted region. It builds up a list of function pointers that it will need later. For example, set file pointer, which is the equivalent of fseek or lseek, and then read file for reading the file, write file for obviously writing a file, and then closing the file handle, and then winexec to execute the file. I mean to execute winword or excel.exe or whatever. And the exit process, which is to kill itself. Sometimes we use exit thread, but And then once it builds up that table of function pointers, it will do a file handle brute force, and then once it finds itself, it seeks to the offset, and then they already know ahead of time how big the Trojan is, so they just read that much and then they write to disk. And typically they'll extract it to the temp folder, and then they run it. Some of the evidence you can see, if you check your temp folder and you see weird exe files or whatever there, that could be it. Yeah. And then it runs a Trojan, and then it relaunches the app to open the clean document and access the current process. And that's it. And sometimes what they'll do is they'll actually have the Trojan, they'll have the clean document inside the Trojan. So, yeah. All right, so So now we go into the tools. What kind of tools do you need to analyze these things? Obviously, these are not PE files, so you can't use a debugger to deal with it. So the tools you'll need is actually very simple. All you need is a hex editor. You can use Hue or Hexer, and a disassembler. You can use also Hue or IDA. And if you want to use a debugger, WinDBG is pretty good. You can use OllyDBG as well. And the objective, when you analyze these things, what you want to do is, first you want to identify the shellcode, and then you want to understand what it does. Most of the time, you really don't need to understand every single aspect of the shellcode, because sometimes you get thousands of these samples, and you don't want to go through and understand every single one of them. Most of them are the same anyways. So, and then you extract the malicious component, typically extracting the Trojan. And if you're an IDS or an AV company, you want to also determine what the vulnerability is. So that's optional, but most people, they don't need to do that. So, all right. So there are two ways you can do it. You can do static analysis. Basically, what you do is you go into a hex editor and you figure out where the shellcode is, and you disassemble it and you read it by hand. You read it manually. Because sometimes the shellcode is pretty complicated. Like they'll do sometimes the decryptor stuff. It's like pretty big and it does all these weird stuff that you don't want to keep track in your brain. So for that, you can use dynamic analysis. So you can actually run the shellcode live, and I'll show you how to do that. So this is the first method. This is from Hugh. I blacked out some of the stuff because I didn't think that was important. So this method is actually pretty cool. So you open up in Hugh, and any of you guys recognize any of these characters? So the first thing you see the E with the like forward accent thingy, that's an OX90, which is a knob. You see the 3, and then like I need to use this. You see this 3 thing right here? So you view this in a hex editor. I use Hue because you can see these things. So you look for these common patterns. You look for like sometimes the knob slice, if they have a huge knob set, so it'll be very obvious. In this case, like the E right here. So you go there and you disassemble it, and if it makes sense, then it's good. If it doesn't make sense, then you go to the next one. The next thing you should pick up is these 3. 3 in hex is OX33, and 33 in Intel opcodes is part of like XOR instructions. We'll typically have 33. So a lot in decryptor stubs, there'll be like an XOR. So you see a lot of XOR. If you notice, you see here it is the 3. Here's another 3. Here's another 3, and a whole bunch of other points. So so they use XOR a lot. And another thing you should notice is this I right here, the I with the 2 dots on the top. This is 8B. So 8B in Intel opcodes is like move instructions. So a lot of shellcodes, obviously when you write assembly code, you need to have moves and stuff. So you can, and that will it'll be 8B. And so you can spot these out. And if you notice, there are a lot of these I's right next to each other. So you know that when you have a lot of moves close to each other, there's a high probability that this is probably legitimate code. Yeah. And another one you should pick out is this one, these 2 things right there. This, the 0O with the delta, like lowercase delta in Greek. This is actually EB, which is a jump. So jump call pop, you'll see these things. So here you see 2 of them. And the next one you should know, this thing right here, the circle with the line. The circle in the line is EA. EA, it's a call. So typically they'll do a backwards call, so it'll be E8, blah, 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 FF, something like that. So you spot those, and it might be a real shell code or something. But the thing is, when you actually, like, most people don't do this because this requires like doing it like 1,000 times for you to recognize these patterns. But when you see these characters in juxtaposition, there's a high probability that it's probably shellcode. One of my colleagues, Christian, he's a virus analyst, and one day he was analyzing some of this stuff with me, and he used Hue, and this guy literally, he just scrolls through like page down, it's like, oh yeah, that's shellcode right there. And I asked him, what the hell, dude, how do you know this? And he's like, oh yeah, dude, like the uppercase E with the forward, the accent mark, that's like encrypted, it's like ingrained in my brain, so I just spot it out. It's crazy, but it works. So you can also impress like girlfriends or something like that with that method too. So, well, a lot of us, like, if you haven't done it for a long time, then you can't, you obviously can't do it that fast. So you got to memorize some opcodes, and so you got to spot out. And you remember EB, which is going to be a jump, E8 call, 8B typically move, 5B. Most of the opcodes in like push or pop, they'll be like in the 5x range, and E2 is a loop, so like here. And also the 33 range, most of the XOR opcodes will start with 33. So when you see all this stuff, close to each other, you have an intuition that it's most likely that they're trying to do something like that's like shellcode-like. So most of the time I ask people whether they recognize, but I'm not going to ask it here because there'll be like an insult or something here. So anyways, and another thing they will use typically though, because to access the base address of kernel 32, they need to look at the tab. So they need to access the tab, which is FS30. And so anytime you, in Intel assembly, anytime when you access a segment, like for FSGS or whatever, you need to have a prefix. So this is a 64 prefix. Anytime you access any instruction that access the FS segment will have a 64 prefix. So you see a 64 and then followed by an 8B, you know that that's a move involving the FS segment, and so you disassemble it. This 64A130, that's like move EAX, like FS30. And then the next one, 648B1D, that's like move to EBX. And the last one, D97424 blah, a lot of the floating point instructions will start with the D9. So like FNSTNV is another way to get the EIP. And this is used in Metasploit encoders, so you can actually spot this pretty easily. Yeah. All right. All right, so once you determine the shellcode, obviously, this I'm gonna go through. These are dynamic analysis techniques. For static techniques, you just page down when you read. Once you identify the shellcode, you just patch the first few bytes with OXCC, which is N3, and then you at startup Office, you attach a debugger to it, and you click on the document, you open it up. And if you identify the shellcode correctly, then you'll hit a breakpoint. But if you didn't, then you'll be screwed because then the shellcode will run, right? So it's important that you run this in a VM or whatever. But of course, everybody here knows that. So yeah. The method two is this one is quite common in the AV business. What these guys do, they'll have like an executable stub. They just copy the shellcode to the entry point and they load it up in their OllyDbg or whatever, and then they single step through it. So that's pretty easy to do. And it's actually very logical to do that. But the last two methods, if you notice, we don't open any file at all, right? The reason why is, because we don't open any file, when the shellcode tries to brute force a file handle, it goes into like an infinite loop, and it sits there and it locks, and then eventually the application crashes. So sometimes, then in most cases, if it can't find itself, then it's not going to be able to extract a Trojan. It's not going to be able to extract a clean document. So you're not going to be able to get the most juicy part of the sample. So these next two methods, you're going to be able to do that. So what you do is you save the files like wherever .bin file. You open up Notepad, calc.exe or whatever, like anything you want, any process you want. You attach WinDBG to it. And then you call .dvalloc. dvalloc, all it does is it allocates a block of memory with read, write, and execute permission. And then you call readmem, and then you basically, what all readmem does is reads the contents of a file into memory. And that's all it does. And so with these two things together, you can say that once you identify the shellcode, you know the physical offset relative from the beginning. And you know where the file is loaded. So the shellcode address is going to be wherever the base pointer plus the physical offset of the shellcode. And then once you figure that out, you just set EIP to that address, and then you single step. And then that's it. Then you'll be like running real shellcode inside debugger. You can also use this method to debug. If you're writing your own shellcode, you can use this method to debug as well. Here it is in action in WinDBG. This is very useful. So if you use WinDBG, is like extremely useful. You should all use it. Method 4. This one, it's pretty easy. Okay. These methods assume that, how do I say this? Sometimes the attackers will know exactly what version of Office you're using, like what locale you are. For example, if they're attacking a German version of Office, they'll like build the exploit according to that. So, but sometimes if you're an AV analyst or whatever, and you like, I don't know, you live somewhere in Japan or whatever, and you don't have a German version of Office, or you don't even know what locale they were targeting. So when you double click on it, it won't run, right? It'll just crash, and you have no idea what's going on. So how are you going to extract the Trojan? So you try to emulate the Office environment. So all you do is you open up a hex editor or like anything that opens the file. You can write your own program to open the file too. And you attach WinDBG to that file, and then you do DVL, you do the same thing. And the advantage of this is that because you open the file, you have a file handle. Even though it's not Office, it's still a file handle is a file handle. So when it brute forces, it'll find itself, and then you'll get the Trojan and the clean document. So this is probably the best method. I use this method every day, I guess. So it's very useful. All right. So that's how you analyze. That's pretty much it. Because most of the time, once you extract the Trojan, all you do is then you do the analysis on the Trojan. You don't care about the office sample anymore. So how to detect this stuff? It's actually kind of difficult, but not impossible. So you need to figure out if you're an IDS, you got to figure out, okay, is this file an ODSS file? If it is, then do something with it. And the way you identify an ODSS file is by the first 8 bytes. It always has DOCF11E0 and blah, blah, blah. And then you fingerprint the application. And by fingerprint, I mean is this a Word document? Is this a PowerPoint document? Is this an Excel? Blah, blah, whatever. And the way you do this is you read the stream name. For example, you see an OLE file with a stream name PowerPoint document stream, then that's most likely to be PowerPoint. If it's Excel, they'll have workbook streams. If it's a Word document, you see a Word document stream. So based on that, you can determine whether the application is Word or whatever. And then you parse the stream content like I showed you earlier. And then you determine the affected records. Most of these bugs are actually in the parsing of the records. So if you know what records are affected, you can actually write a signature to detect this exact vulnerability. And so the UFP rate will be much lower. So here we go. So you can download the specs from this website, or you can just go to live.com and search for Microsoft Office specs. It's usually first or second hit or something like that. And so given the documentation in here, you can actually write your own parser. And like I said, it gets updated quite often, every month, sometimes every 2 months. So it's very, very useful. And this. So map is, let's say that you don't have your own parser. Let's say that you try to reverse engineer the patch. But most people, when you bin diff a patch, you can figure out, okay, yeah, this is a buffer overflow. But in Office, in order to exploit the vulnerability, you actually need to know what specific record is bad, right? So without that knowledge, it's very difficult to craft your exploit. So you need to know the file format so that you can write your exploit. And bindiff obviously is not going to show you that. And at the assembly level, it's very difficult to figure out what type of record what type of record you need. So in order to write good signatures, you need to figure this out. Because if you do generic, you'll get FPs all over the place. So you have 2 options. You can either reverse engineer the patch and I don't know, pray and work really hard to figure out the the record type, or we'll give you the vulnerability details. So if you work for an AV or an IDS company, we'll provide these things. And this is the Microsoft Active Protection Program, aka MAP. I actually work on the team the team that produces this data. So I deal with mostly PowerPoint stuff. So if a PowerPoint, anything to do with the kernel, network stack, RPC, whatever, it'll be me. So if you can complain or hug me if you want. All right. So what do you get with this MAP program? You get a technical description of vulnerability, a repro file. I'll actually generate a file because I already know what the record is. A repro file, if it's a network vulnerability, I'll give you a packet trace. And then, then it'll be a no-brainer. And then we'll also give you a crash dump, or even a stack trace, a disassembly, and sometimes I'll include annotations of the disassembly, because obviously I can't give source code. So I'll annotate the disassembly so that people understand, what the vulnerability is. And also I'll give detection logic, which is implemented in this detection logic. Basically, I'll give you it'll be a C-like program that you pass a file in and you run it against this program, and it'll tell you whether the file is vulnerable or not. And most people, a lot of our MAP partners, they'll take this, they'll translate it into their own engine language because it's very C-like, and then they just deploy it. So here's an example. This one is pretty old, so I can say it now. This is an Excel vulnerability, and this is what you'll get. This is a technical description. We tell you that this is an uninitialized stack, uninitialized memory vulnerability. We'll tell you that the exact records that are being affected, and we'll give you the detection guidance. And with all this stuff, if you're not lazy, you can translate a lot of this. You can take this, translate to your IDS or AV. Yes? Well, are you gonna hug me or what? I mean, that depends. Right? Are you gonna hug me or like complain? Oh, so this I actually didn't write this. This a colleague of mine wrote this. So, anyways, yeah. And then this one I wrote. This one is in the PGM protocol. So, yeah. Then we tell you exactly what it is. And I'll give you a packet trace. This is this is like Wireshark or something like that. And I'll, so that you can figure out the vuln, just in case you don't want to generate the packet yourself. So with all this information, it's like a no-brainer to implement this. Acknowledgement, I want to thank Rob, Jonathan, Damien, Fermin, Brian, Christian, Nick, and the office team. And many other people who don't want to be acknowledged. And so... And so one last thing, so we have a blog where we talk about the vulnerabilities. Sometimes we actually give all the details of vulnerability. Like, for example, in some cases, I think we even released a disassembly and we'll tell you exactly where the vulnerability is. So it's like blogs.technet.com/swy. It's actually written by the people who triage these bugs. And if you have bugs to report, send it to secure@microsoft.com. And if you have like interesting office samples that you don't want to analyze or you want to help in triaging, or if you think it's a 0-day, send them to me if you want. And my email is just 3 letters, like bda@microsoft.com. And that's it. So OX3F is the question mark. So if you have questions, please do ask. No questions. Wow. Are you joking? Oh, by the way, I want to say one thing. It's like, I've never seen so many Mac users before.
So you were saying that in order to detect what application it was, one should look at the stream name.
Correct.
That sounds like a heuristic that might be different from the one that is used to actually determine the application that the user invokes. Now, I don't know the internals of Office applications, but that to me sounds like a way which would let me build a file that is an Excel sheet to the virus scanner and a Word document to Word, and then includes 2 streams. Maybe I'm wrong, just wondering.
So I guess, help me understand the question. Here, you're saying...
Let me try to rephrase. Is it possible to build a document, given the advice that you gave, that would be in which one set of streams would be read by the IDS and found good, and a different set of streams would be read by the productivity application, and oh shit, it includes the 0-day.
Ah, I see. You probably can't do that because if the stream name is wrong, for example, if it's a PowerPoint document and you don't have if the stream name is not called PowerPoint document stream, PowerPoint is not going to open it because...
I've got 2 streams in it.
Pardon?
I have 2 streams in it.
It doesn't matter if you have 2 or 3 streams. It's based on the name. Like they will actually open the stream name. It's hard. It's actually in the spec. If all PowerPoint documents must have the stream name. So the probability of you getting an FP is pretty low. It could happen, but it's pretty low. I mean, you could go and generate a PowerPoint document with a stream name in there, but I mean, you could do that if you want. I don't see why not. But what I'm saying is the advice I gave, the FP should be very low. I'm sorry if I misunderstand the question.
Just a follow-up on that. Over here. It is possible to make a document with the appropriate streams for multiple ones, and it will open in both.
Yeah.
And it is theoretically possible to use this to confuse scanners into missing embedded content.
Is there any? So I'm not understanding this. This is like you were saying, like, it's theoretically possible to craft a document that can be that doesn't have the appropriate stream name, but can be opened by Office.
Have the appropriate streams.
Yep. Yeah, exactly. You can
It just
embed
has
an Excel
multiple
document
streams?
inside a PowerPoint document. You'll have the valid stream. Yeah.
Yeah. But
Is it? Sorry. Sorry. I just want to make sure that I'm explaining it correctly.
yeah, this is something I probably shouldn't be talking about.
Yeah. Yeah. I mean, don't mean no. You can come talk to me after if you want. I mean, I'll explain it to you. Yeah. So, is that it? Okay. That's it. Yeah.